Hi all, and welcome to day 7 of Advent of Elixir. Today we're going to go a little bit under the hood of the Beam virtual machine and talk about Elixir and Erlang bytecode. So here we have our Advent project, and I'd like to focus your attention on the build/dev/lib/advent/ebin directory. Elixir is a programming language that compiles code. And this is where the compiled artifacts wind up. Note that there's a file elixir.advent.beam that I'm going to highlight. And this is the compiled version of the module with the code here. It's a binary file, so the VS Code editor is not going to go ahead and show us, but we'll take a look at it later. To prove to you that this is the artifact, one of the things I will do is I will quickly build another module. We're going to then recompile. And you'll see that another Beam file appears. And conversely, if I delete that module and recompile, that file disappears. For those of you who don't know, the alias A advent is short for the atom elixir.advent, and I'll demonstrate that here. And you can see that these are the same. And that's why this Beam file has E elixir in front of its name. Okay, so now let's take a look at this file directly. Instead of using the text editor, I'm going to use a hex editor. And for those of you who are not familiar with how hex editor works, on the left-hand side is a hexadecimal representation of the binary contents of the file. On the right-hand side, where possible, it decodes the text into valid ASCII. There are going to be some places where that's not possible. For example, 00 is not an encodable ASCII value, and so you get this little gray dot. So the first thing you should notice is that in a Beam file, you've got this FOR1. This is a magic cookie, or a special value that indicates that this file has a file format called IFF. And IFF is an old format from the 1980s invented by the company Electronic Arts for generic data interchange between computers of different architectures. For some historical reason, the Erlang virtual machine decided to use this format to store its Beam modules. And so that's what we've got today. Fun fact, SimCity 2000 also uses the IFF format for many of its save files. So as a trivia question, you can know that that is what SimCity 2000 and Elixir and Erlang have in common. One of the key things about this IFF format is that all data are chunked into 32-bit segments. So each one of these is 1 byte, or 8 bits. 4 of them together make 32 bits. And so you can just walk down this file 32 bits at a time, and certain things will fall out. For example, you can see this BEAM there. That is a chunk that signifies that this file is a file formatted, a subformat of the IFF format, which is the Elixir or Erlang Beam module. Then there are certain parts where they have special magic characters that indicate the beginning of certain sections. For example, this ATU8 is a UTF-encoded atom section. And here you can see a bunch of UTF-8 encoded atoms. So elixir.advent, which is the name of the module, that's an atom. And we see a bunch of function names, __info, and further down, module info, which are function names that are placed in this atom table because every time you refer to a function, you refer to a function using its module, its function name, and arity, and the module and the function name are both atoms. So these atoms will necessarily need to be inside of the atom table. Let me demonstrate that really quickly. I'm going to make a function, and it's going to return the hello atom. We're going to recompile that. And what we should see is we should see both the func and the hello atom appear in this ATU8 section. And you can see we've got func right there, and we've got hello right there. After the atom section, we have something called the code section. And this section contains the binary encoded code that actually gets executed. There are a few more sections: strt, which is a section that holds Erlang strings, impt, which is a list of imports, expt, which is a list of exports, litt, which is a table of literals, loct, which is a table of locations, attr, which is a list of attributes. And this one is interesting because you can see the version 8.2.1 sitting in here, and also the VSN value over here, and various other important things like module compiler metadata, and also furthermore sections like debug info, dbgi right here, and also some documentations in the docs section, and so on and so forth. So to get a little bit more insight into what's going on, we're going to have to use a different tool. I think it would be pretty difficult to be able to look at this code segment here and deduce what exactly is running inside of your module. Moreover, it's important to note that the format that this is saved in onto disk is a format that is optimized for saving content to a disk in the context of a interchange format that is optimized for interchanging data between systems of different architectures. That's not necessarily how you want to store your data in memory. And in fact, when you load a module from a Beam file, Erlang does a transformation to convert it to a completely different binary value than what exists in these Beam files. So let's see if we can't get at that. Well, the key thing that we're going to need is a function called code.getObjectCode. And we pass it the module name. And this gives us a triple. The triple is the module name, the internal memory binary for the module, and then the path to the module. So we're going to pull the second element out of that. And then what we're going to do is we're going to run this through another function in the Beam Disassembling module. Now, the Beam Disassembling module is a module that contains tools, well, specifically one tool, to help you disassemble this in-memory data format and break into it and turn it into the code that actually gets run. So let's quickly take a look at that. And the function you run is file. So when we pass the module into that pipeline, we get a breakdown. And here, it's a triple of Beam file, the module name, then a bunch of exports. So this is a list of all of the functions that outside code can use to access inside the module. So we have the name of the function as an atom, the arity of the function, and this number here is the entry point, and I'll explain that in a bit. But here you can see info and module info, which I discussed in the video that I'll link to below. And we also see the func function that I created, which is a zero arity function. Then we have module attributes. Remember the VSN that showed up when we inspected the attributes in the previous video? And also compiler metadata right here. What follows is a reorganized version of all of the code that that exists for the functions. And the way to read this is to look through these labels. These labels are what we call entry points, and there are spots where you can jump into the code. Then these lines are just kind of metadata that exists, so we can ignore them. I'll go over this opcode later, and basically everything past here is everything that isn't either a line or a label is something that we call an opcode. And that's an instruction for the virtual machine to run. The one last thing to know before we go on is that the virtual machine is something called a register machine. We don't ever save variables like x, y, or value, or whatever you want to name it, con. What we will do is we will have a series of a bunch of slots starting at the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so forth. And into these slots, we can temporarily store values. And those values can be any value in the Beam ecosystem. They could be a number, they could be a PID, they could be a string, they could be an atom, they could be a map. Whatever you want that is a valid data type in Elixir or in the Beam can be placed into one of these slots, which we call registers. And what we're going to go over is see how manipulating these slots results in doing things that you care about in the Beam. So let's first take a look at this func function, which I've written, which just returns the atom hello. Now, if we look up here, we see that func is a zero-arity function, and it jumps into the entry point at label 11. And sure enough, if we look at the function func here, it is repeated that it is a zero-arity function, and it jumps in at label 11. What does it mean for it to be a zero-arity function? What that means is that we're going to take the list of arguments and put none of them into the registers. So the registers should all be completely clear. We're going to jump to label 11 and not label 10, which I'll explain in a bit. But label 11 is here, and then we look at the next instruction. But this instruction says move the atom hello into the 0 register. So remember, the 0 register, we don't know what it had, didn't have anything in it. And then we put the atom hello into that register. Then we do return. And what return says is take whatever is in the 0 register and use that as the return value for your function. So you can see how this set of 3 instructions encodes the action of defining a function that returns hello, taking no arguments at all. Let's do something a little bit more complicated. Let's do some math. So what I'm going to do is I'm going to add A and B, and then we're going to return that value. Then let's find what got created. And here we have the add function. It's an arity 2 function, and it starts at label 11. Label 11 is here, and we have one instruction before the return. This is a garbage collected built-in function called add. This F0 says what you should do when you fail. We're not going to worry too much about that. And then it says you can garbage collect. You should create, before jumping into this function, you should create 2 extra slots that can be garbage collected. We're going to put x0 and x1 into the slots, and these are going to become register 0 and register 1 for the plus function. Then take the result of the plus function and drop it into the 0 register. So remember, add was a 2-arity function, so A got put into register 0 and B got put into register 1. Now those 2 arguments got put into register 0 and then 0 and 1 got put into the register, the 2 call positions for the plus function, and the result, which should be A plus B, wound up in the 0 register, which then got returned. Just to show you what would happen if I did B plus A instead, the add function now puts what was in register 1 as the first argument, so that was B, this is register 1, as the first argument of the plus, and the second argument of the plus gets register 0, that's A. So these two positions are swapped, which is what you would expect since I swapped the order of these arguments. Let's do a little bit more math so we can see something a little bit more complicated. I'm going to do math. It's going to take one argument only. We're going to do temp equals 2 times A, and then we're going to return A plus temp. Recompile it and take a look at what code results. And here's the math function, jumps in at position 11 again. We've got a garbage collected built-in function multiply. We only need to make one extra slot because we're passing only one variable in. This is the literal integer 2. So this doesn't need to be garbage collected when we come back. Basically, what it's saying is take the 0 register, which in this case contains A, then pass that along with the literal integer 2 to the multiply function, and put the result in register 1. So now register 0 still contains A, and register 1 contains 2 times A. So this register 1 is basically the temp variable. Then we do the plus operation, and this gets a little bit complicated. I will explain this in a moment. But x0 is, as we said before, contains the value A, and x1 contains the value temp. Put the result in x0, and that gets consumed by the return statement, and that becomes the result of the whole function. Now, what is this tr number 0, 18, blah, blah, blah? That, I believe, is a new feature which instructs the system that this whole thing can potentially be executed with the new Erlang JIT compiler. And very likely the reason why that got included was because the analysis system noticed, hey, the result of a multiplication is very likely to be a number, and the inputs to a plus are very likely to be a number as well. So if these are the case, then go ahead and jump into some sort of JIT compiled code, which will execute faster. Great. So let's do another function where instead of calling these built-in functions, something is going to happen where we call in a function that exists in another module. So I'm going to do io.puts. We're going to recompile again. And let's take a look at the code. So here greet is a function with one arity that jumps in at label 11. So that's here. And here it just does a call x only. So this is an external call. The external function that it's going to call is io.puts, which has arity of 1. And notice that because message is the same, has the same register, it just goes ahead and it doesn't need to move that out of register 0 because it knows that io.puts is going to consume register 0 as its first parameter. This is basically a tail call, and it will basically be able to just substitute the greet function for the io.puts function. Now, what would happen if I added an extra parameter here? Now we take a look at the greet function. And we don't know what's going to be in register 0. It could be whatever we pass here, but the key thing that we care about is the message, and that's in register 1. So here, the first thing that we have to do is we have to move the contents of register 1 into register 0 before handing the whole thing over to io.puts so that io.puts can consume its view of register 0 right here. So that's how you can move things around between registers to give functions what they expect. I want to take a look at one more thing, where we're going to do a greet except with a Boolean value. So we'll do that, and then if bool do io.puts hello, else io.puts bye. Let's recompile this again and take a look at the code. And this is going to be probably the most complicated thing that we're going to look at here. But what it'll do is it'll demonstrate how labels are used. So this greet function here now jumps in again at 11, and it has one parameter. That's going to be an x0. So what we're going to do is we're going to do this select val opcode. And what select val is effectively a case statement. It's going to look at what was in the 0 register, which is the parameter of the function. And then if it fails, i.e. it can't find the value, it's going to go to label 13. We'll get to that in a second. The list of things that it's going to check against is the atom false, in which case you should jump to label 12. The atom nil, in which case you should jump to label 12. And remember, false and nil are the two falsy values in Elixir. So what we're going to do is we're going to check, hey, is it false or if it's nil? If it is, then jump to 12. Label 12 is here. Move the literal string by into the 0 register, and then go ahead and call io.puts. And this winds up functioning as if it's a return. So note that there's no return statement in this function, and it says swap this function in for io.puts. So basically what we're doing is we're moving the literal by into the 0 register and having io.puts adopt that 0 register. If it's neither false nor nil, we fail to select on any of the values in this list, right? So it's going to go and fail to tag number 13. So we jump to tag label 13, in which case we put the literal hello into the 0 register, and then we call the same call x only, which is io.puts, and we have we tail call into io.puts with the literal hello as what exists in the 0th register for this function. So I know this subject has been a little bit more difficult, especially if you're a beginner Elixir developer. But for those who are more intermediate and advanced, you can get a mental model of exactly what is going on under the hood when you write functions in Elixir. There's a lot more to this than what I've shown you here, but this should kind of give you a taste of what's going on, and also like an easy entry point for you to figure out and experiment on your own and take a look at what your disassembled code looks like. I think this stuff is really powerful. In particular, I learned this because I was working on a project to do type checking in Elixir, which I know is a larger project that Jose Valim has endorsed. I may come back to that in the future because I think some of the stuff that I discovered is really useful and may wind up being a very effective way of doing type checking, especially since the type checking that I was doing was theoretic along the lines of what Jose wants to encourage research into for the Beam virtual machine. Hey everyone, this is Isaac. Sorry, I was editing the video and I realized that I had forgotten to explain something. And the thing that I forgot to explain was what is going on with these extra func info opcodes that sit in a label before the actual body of the function. And what that is a mechanism for Erlang to add stack trace information onto your stack trace in the event that something terrible has gone on. So for most part, you kind of don't really need to worry about this opcode. Just know that it's there to add stack trace information for debugs. I also have one more piece of information to mention, and that is that I am going to start a Patreon for these videos. I'm going to put a link to the Patreon below, as well as a link to another nice resource that is unfortunately a little bit incomplete. It's called the Beam Book, but it should have more information about how to interpret opcodes and how to interpret the binary formats that I discuss in this video. So look out for a link to the previous video, some information about the Beam Book, and also a link to the new Patreon that I'm making. See you tomorrow.